entropy, thermodynamics, and why time has direction. You cannot unbreak a coffee cup. That sounds obvious, almost insultingly obvious. But stop and really think about it for a second, because buried inside that simple fact is one of the deepest mysteries in all of physics. The laws of nature, at their most fundamental level, are almost perfectly reversible. A particle moving forward in time follows the same equations as a particle moving backward in time. Gravity doesn't care which direction time flows. Electromagnetism doesn't care. Even quantum mechanics, for the most part, treats past and future with remarkable indifference. And yet, you have never, not once, seen a shattered coffee cup leap off the floor and reassemble itself in your hand. You have never watched a scrambled egg unscramble. You have never seen smoke pour back into a chimney and turn back into wood. Time, in every experience you have ever had, flows stubbornly in one direction. Forward. Always forward. So here is the question that should keep you up at night. If the fundamental laws of physics are reversible, why isn't the universe? The answer to that question takes you on a journey through thermodynamics, probability, information theory, and the ultimate fate of everything that exists. And by the end of this, you will understand something genuinely profound, not just about physics, but about why you experience life as a story with a past and a future, rather than a timeless, directionless blur. Let's begin. The arrow of time. A problem hidden in plain sight. Back in the 19th century, physicists were grappling with steam engines. This was the industrial age, and the practical question on everyone's mind was simple. How do you get the most work out of heat? But in trying to answer that engineering question, scientists stumbled onto something far deeper. A French engineer named Sadi Carnot, and later a German physicist named Rudolf Clausius, began noticing something strange. Heat, they observed, always flows in one direction. Hot things cool down. Cold things don't spontaneously heat up. A cup of hot coffee left on your counter doesn't get hotter while the room gets colder. It's always the other way around. Always. Clausius, trying to capture this observation mathematically, invented a new quantity. He called it entropy, and his description of it, stripped to the math, goes something like this. In any natural process, entropy either stays the same or increases. It never decreases on its own. Never. He called this the second law of thermodynamics. Now, here is where things get philosophically explosive. Because notice what Clausius has just done. Every other law of physics up to that point was symmetric in time. Throw a ball, and the equations describing its arc work just as well if you film it and play the film backward. But the second law is different. It says the universe has a preferred direction. Entropy goes up, not down. The future is the direction of higher entropy. The past is the direction of lower entropy. Clausius, almost without realizing it, had discovered the physical origin of time's arrow. But what is entropy, really? The word gets thrown around a lot, and it's usually described vaguely as disorder or chaos. That's a start, but it's not quite right, and the real answer is much more interesting. What entropy actually is. Imagine you have a box divided in half by a partition. On the left side, you put 100 red gas molecules. On the right side, you put nothing, a vacuum. Now you remove the partition. What happens? The red molecules rush into the empty space, spreading out until they fill the whole box roughly evenly. That's obvious. But now ask yourself, why don't they spontaneously rush back to the left side? The physical laws governing each individual molecule don't forbid it. Every collision, every bounce off the wall is perfectly reversible in principle. So why does the gas never go back? The answer is probability. And this is the insight that a brilliant Austrian physicist named Ludwig Boltzmann contributed in the 1870s at great personal cost. He was so ridiculed for his ideas that it contributed to his depression and eventual suicide. History vindicated him completely. Boltzmann's insight was this: entropy is not about disorder in some vague aesthetic sense. Entropy is about counting. It is a measure of how many different microscopic arrangements of a system correspond to the same macroscopic appearance. Think about it this way. There is only one arrangement of those 100 molecules where they're all huddled in the left half of the box. But there are an astronomically large number of arrangements where they're spread roughly evenly throughout the whole box. When you remove that partition, the molecules start bouncing around randomly. They're not trying to spread out. They're not obeying some law that says spread out. They're just moving randomly. But because there are so vastly many more arrangements that look spread out than arrangements that look all on the left, the system almost inevitably ends up looking spread out. It's not a law. It's overwhelming probability. Stop. Think about that for a moment. The arrow of time, the reason past and future feel different, the reason you age in the universe runs down, is ultimately a statement about counting, about the sheer staggering difference between the number of ways things can be messy versus the number of ways they can be ordered. Boltzmann captured this in what became one of the most beautiful equations in physics, carved on his tombstone in Vienna: S equals K times the logarithm of W. Entropy equals a constant times the logarithm of the number of microscopic states. Simple, devastating, profound. The coffee cup and why you can't go back. Now let's go back to your coffee cup. When it sits intact on your table, every atom is in a very specific, very precise arrangement. The ceramic molecules are bonded in exact positions, forming a smooth, curved wall. There are relatively few microscopic arrangements that correspond to intact coffee cup. It's a highly ordered, low entropy state. When you drop it and it shatters, the pieces spread across the floor. Now the atoms are distributed across a vastly larger region of space in a vastly larger number of possible configurations. There are enormously more ways for the atoms to be arranged in a shattered cup state than in an intact cup state. For the cup to spontaneously reassemble, all those atoms would have to happen to move in exactly the right way, at exactly the right time, with exactly the right energy to reform those specific molecular bonds in that specific shape. The probability of that happening by random thermal motion is not zero, but it is so incomprehensibly small that if you waited for a time many times longer than the current age of the universe, you still wouldn't expect to see it happen even once. This is what irreversibility means. Not impossible, just so staggeringly improbable that for all practical purposes and for all cosmological purposes, it never happens. The same logic applies to aging. Your body is an extraordinarily ordered arrangement of matter, atoms in precise configurations forming proteins, cells, organs, a nervous system. Every second, random thermal fluctuations and chemical reactions push toward disorder. Your cells were constantly using energy to maintain that order, but the maintenance is imperfect. Over time, entropy accumulates. Errors build up. Structures degrade. This is aging. Not a mystical process, not a curse, just entropy, doing what entropy does. You can't reverse aging for the same reason you can't unbreak the cup. The number of ordered, youthful molecular configurations is vanishingly small compared to the number of degraded ones. You can slow it, you can repair some of the damage, but you cannot spontaneously move from high entropy to low entropy without spending enormous amounts of energy elsewhere. And here's the kicker: when you do spend that energy to create local order, you always increase entropy somewhere else in the process. Your body's metabolism creates heat, exhales carbon dioxide, produces waste. Net entropy always goes up. You can cheat locally, temporarily, but the universe always collects its debt. But here's where it gets interesting. The low entropy past now, you might be thinking, okay, entropy increases, things fall apart, I get it. But there's a deeper puzzle lurking here that most people never ask about. Why was entropy low in the first place? Think about it. The second law says entropy increases. But for entropy to increase, it had to start low. Your coffee cup had to start intact before it could shatter. The gas molecules had to start on one side of the box before they could spread out. The universe had to start highly ordered before it could become disordered. And the universe did start in an extraordinarily low entropy state. The Big Bang produced a cosmos that was, in thermodynamic terms, almost impossibly ordered. Smooth, hot, dense, uniform. As the universe expanded and cooled, gravity began clumping matter together into stars and galaxies. Stars are, in a sense, machines for exporting entropy. They take nuclear fuel, hydrogen, in a concentrated, low-entropy configuration, and they burn it, radiating high-entropy heat and light in every direction. The sun is doing this right now. Every photon of sunlight that hits the Earth is a packet of low-entropy energy. Plants absorb it and use it to build ordered structures: glucose, cellulose, the architecture of life. Animals eat plants, inheriting that order, using it to power their own improbable molecular structures. Everything eats sunlight, ultimately. And everything exhales entropy. You are, in a very real sense, a temporary pocket of order in a universe flowing toward disorder. You exist because 14 billion years ago, the universe began in a staggeringly low entropy state, and we are still, slowly, burning for that inheritance. The physicist Roger Penrose has calculated just how improbable that initial low entropy state was. The number he arrives at is so large it makes the mind go blank. A 1 followed by 10 to the power of 10 to the power of 123 zeros. This specific ordering of the early universe wasn't just unlikely, it was cosmically, almost incomprehensibly unlikely by any random selection. Why was it that way? That question is still open. It may be the deepest unanswered question in physics. Entropy and information, the surprising connection. Now we need to talk about something that will make this whole picture even stranger and more beautiful. In the 1940s, a mathematician named Claude Shannon, working at Bell Labs on the problem of transmitting messages reliably, developed a mathematical theory of information. He wanted to quantify how much information a message contains. And the formula he arrived at was, to put it gently, shocking. It was identical to Boltzmann's entropy formula. Not similar, not analogous, mathematically identical. This was not a coincidence. It turns out that entropy and information are two sides of the same coin. When a system has high entropy, many possible microstates, you have high uncertainty about which microstate it's actually in. That uncertainty is information. The information you would gain if you somehow knew the exact state. Imagine that gas in a box again. When all the molecules are on the left, you know roughly where they all are. Low entropy, high information about their location. When they spread out randomly, they could be anywhere. High entropy, low information about any individual molecule's position. This connection has deep implications. It means that erasing information, truly irreversibly destroying it, always increases entropy. This was proven by a physicist named Rolf Landauer in 1961, and it's called Landauer's principle. Every time a computer deletes a bit of information, it must release a tiny, tiny amount of heat into the environment. Computing has a thermodynamic cost. Thinking, in some sense, has a thermodynamic cost. There's a beautiful thought experiment that illustrates the connection between information and entropy. It involves a tiny imaginary creature proposed by James Clerk Maxwell in 1867, known ever since as Maxwell's demon. Imagine a box of gas divided in half with a tiny door between the two halves. A small demon sits at the door. Every time a fast molecule approaches from the right, he opens the door, lets it through to the left. Every time a slow molecule approaches from the left, he opens the door, lets it through to the right. Gradually, fast molecules accumulate on the left, slow ones on the right. The left side gets hotter. The right side gets colder. Without doing any mechanical work, the demon has separated hot from cold, apparently decreasing entropy. Carnot and Clausius would be horrified. Have we violated the second law? No, because the demon has to measure the molecules. He has to store information about which ones are fast and which are slow. That stored information has an entropic cost. And crucially, at some point his memory fills up and he has to erase it to keep working. And that erasure, per Landauer's principle, releases exactly enough heat to restore the entropy the demon seemed to have destroyed. The demon fails. The second law survives, but the way it survives reveals something astonishing. Information, knowledge, measurement, these aren't separate from the physical world, they are part of it. They carry thermodynamic weight, heat, death, and the ultimate fate of everything. Let's zoom out now, all the way out. The universe is running down. Entropy is increasing everywhere, all the time. Stars are burning through their fuel. Galaxies are slowly spreading apart. Structures gradually giving way to sameness. The process is slow, almost unimaginably slow. We are roughly 14 billion years into the life of the universe, and things still look quite lively. But the trajectory is clear. In the far future, trillions of years from now, the last stars will exhaust their fuel and die. black holes will slowly evaporate via Hawking radiation, a process that takes an almost incomprehensible amount of time. Eventually, nothing will be left but cold, thin, evenly distributed radiation and particles, a universe at maximum entropy, with no temperature gradients, no free energy, no structure, no events. This endpoint is called heat death. Not hot. The universe will be extremely cold. The word heat here refers to thermodynamics. Heat death is the state of thermodynamic equilibrium. A universe where nothing ever happens again, because nothing can happen without a difference in entropy somewhere to drive it. It sounds bleak, and in one sense it is. But here's another way to think about it. The very fact that we exist, that you are sitting here contemplating your own existence, that stars shine and planets form and life complexifies and minds wonder, all of this is only possible because the universe isn't at equilibrium yet. We live in the lucky, transient, beautifully ordered middle of a story that began with impossibly low entropy and is slowly burning its way toward maximum entropy. We are not the tragedy of entropy. We are entropy's most spectacular detour. While you experience time moving forward, so now, finally, we can answer the question we started with. Why do you experience time as flowing in one direction? Why do you remember the past but not the future? Because your brain, like everything else in the universe, is an entropy-increasing process. Memory works by recording information, creating ordered, low-entropy structures in your neurons that correspond to past events. The past has left traces everywhere, in your memories, in physical records, in the state of the world. The future has left no traces because it hasn't happened yet. The arrow of causation, the arrow of memory, the arrow of time, they all point in the same direction as the arrow of entropy. But here is the truly vertiginous part. Your subjective experience of time flowing, the feeling of the present moment, the sense of now moving forward, may itself be a product of entropy. Each moment, the universe moves into a slightly higher entropy state. Each moment is, in a subtle but real sense, different from and irreversible from the last. Your consciousness, tracking those changes, experiences them as the flow of time. There is no special physics of now. The present moment isn't written into the equations. What's written in is entropy. And entropy, pointing relentlessly from low to high, from past to future, gives time its direction, gives your experience its structure, gives the universe its story. Richard Feynman, who spent his career stripping physics down to its essential strangeness, once said something that captures this beautifully. He described the quest to understand nature not as memorizing facts, but as learning to see what is really there, the deep structure beneath the ordinary appearance of things. Entropy is exactly that kind of insight. Ordinary things. Ice melting, coffee cooling, cups breaking, people aging, are windows into a cosmic truth about probability, information, and the direction of time itself. The wonder of what we know. So let's take stock of what we've actually learned. Time moves in one direction, not because the laws of physics force it to, but because of overwhelming probability. The past was a state of low entropy. The future is a state of higher entropy, and there are almost infinitely more high entropy states than low entropy ones. So that's where things go. Entropy is not vague, disorder. It's a precise count of the number of microscopic arrangements that correspond to a given macroscopic appearance. More arrangements equals higher entropy. Information and entropy are mathematically identical. Erasing information generates heat. Your demon cannot outsmart the second law. And the universe began in an improbably low entropy state. So improbable it staggers the imagination, and has been spending that ordered inheritance ever since. We, and everything we love, exist in the window of time between that improbable beginning and the heat death that waits at the end. What do you do with that knowledge? Maybe the same thing you always do when physics strips away the familiar and shows you the strangeness underneath. You sit with it. You let it expand your sense of what's real. You feel maybe a little differently about your coffee cooling on the counter, about the passage of time, about the improbability of being here, conscious and wondering, in the narrow slice of cosmic history where entropy hasn't yet erased everything interesting. The arrow of time isn't a limitation, it's a gift. It's what makes stories possible. It's what makes memory possible. It's what makes change, growth, experience, life itself possible. In a universe at maximum entropy, nothing happens, ever. But we don't live in that universe. We live in this one, still burning, still churning, still full of ordered pockets pushing against the tide. And for now, that is everything. If this left you wanting to go deeper into quantum mechanics, into the information theoretic foundations of physics, into the strange world where thermodynamics meets black holes, there is so much more waiting. The universe rewards the curious. It always has. Keep asking why.